All right. Um, cool. So I want to start out just reviewing what we did yesterday with Jesse. Jesse gave you a really wonderful intro to the Colab and Jupyter Notebook interface and to Python itself. And I just want to upfront say that I use Jupyter, but I don't use Colab, and there's enough differences between them that you might see me struggle. And that's great, because then we can all learn from my mistakes. So you might see me poke around and not know where the buttons are, and that's because I don't use this interface. And so hopefully anything that I learn, you'll learn as well. Cool. So normally in a Colab notebook, like the one that we're looking at, towards the top, it would be filled with import statements. And we talked a little bit about this, but these are the statements that allow you to use other libraries in your own code. And so math is an example. I'll show more of these later. But I just want you to understand that the notebook that you're seeing is great for this tutorial, but it's not necessarily like a typical notebook would be, and that a lot of the stuff that you would see at the top is not typically there. But we'll talk more about that later. And let's start with the reviews. So we talked a lot last time about variables and comments. And so I'm going to just kind of quickly go over those to make sure that we're all on the same page again. In Python, it is usually good to try to follow what's known as the Python style or PEP and PEP 8. And what that means is that variable names will usually be in lowercase, and they'll, if you want to do a two-word variable like Avogadro's number, you would write Avogadro underscore number. Like that would be the variable name that would be useful. And other words, though we talked about a bunch of these yesterday, are called reserved words. And I'm showing you a table of some of reserved words now, and we're going to get to a few of these today, and they're actually quite important. So I just want to point them out. Import, right? We talked about that. That imports a library, and so it would make sense that that's not available as a variable name to me, right? Because Python needs to be able to distinguish internal things from things that you're trying to tell it, like variable names. And then true and false, notice the capitalization there is important. If and else, we'll talk about that today. And things like and, or, not. And so there's a list of these words that you cannot and should not use as variable names. But other than that, you have a fair amount of freedom. And like I said, the general, it's generally good form and good practice to use variable names that are lowercase. And if they're multi-word, use an underscore instead of a space. So let's see an example. We talked about floating point numbers. And so here I have an example of pickles, which I've set to be the value of 3.14, which is an acceptable but meager estimate of pi. And so if I execute this cell, I get the output 3.14. And so the first line, we set the variable pickles to the value 3.14, which is a floating point number. And if you remember, that means that the decimal point can float. It doesn't have to be in a fixed position. And the print statement causes it to print out the value of that variable pickles. All right, great. We talked about a lot of that yesterday. Now, what if what if I'm reading your code and everywhere that you wanted to have the value pi, you had the word pickles? What am I going to think about when I'm reading your code? Well, I'm probably going to think about I'm hungry and I want some pickles. But I'm not going to recognize the word pickle necessarily as being the value of pi. And so it's important to think about your choice of variable names. And again, Jesse hinted at this yesterday, and that some variable names are better than others. And so what I probably should do, instead of calling it pickles, I should probably call it something like pi, right? And so that's much more informative to the user, to the next person that comes along and reads my code, what my intention was with that variable name. So we did talk a little bit about floating points. And there's a point that I want to make that might not be readily evident from those internal representations that we talked about, which is how computers store numbers. But they don't actually store the numbers in the precision you might think they do. And so if you see here, I have this thing, 10.0 times 0.1 equals 1.0. You can try that out, and we could do that right now. We could say 10.0 times 0.1 And it looks on the screen like it equals 1.0. And it may very well inside of a computer, but the truth is it also may not. So it's possible that this number could be represented in the computer by a number that looks much more like, oh, right? That inside of the, yeah, perfect. So Python did exactly what I wanted it to do, right? When I have the number 0.9999999, what Python is going to want to do is show that as 1.0. Now remember, inside the computer, that's represented as 0.99999. And so if I were to try to run this statement here, if I were to try to test this statement as a test, it might say false. It might tell me that these are not equivalent. And that's because internally, the calculation that has been done yielded 0.999999, which is really, really close to, but not exactly 1.0. So I want you to just, the takeaway from this is be really careful when you're thinking about floating point numbers, that is numbers with a decimal point in them, is that testing them for equality in a computer program can be a very fraughtful thing. You may think it makes perfect sense, but in your head, you have to remember that the computer may have a slightly different representation of the number that you're trying to test. And so this example here in cell 5, I think demonstrates this nicely, is that to us, the computer shows us that number is 1.0, but really deep inside, the memory representation is this value. Okay, does that make sense? Any questions? Okay. That's actually a thing that gets people hung up long into their careers. And so I want to bring it up early so that at least you're thinking about it in the future. Okay, and here, since we called pi 3.14, let's actually define pickles as what they are, a cucumber preserved in vinegar or brine. So now we have our value for pickles set to the definition of pickles. So we'll come back to that. Great. So here's an example of some comments. We remember a comment is something that goes into a code cell and begins with the hashtag. I grew up calling it a pound, whatever you want to call it, but that denotes the beginning of a comment in Python. And so as remember Jesse said yesterday, if I execute this code cell here with the example comment and this value commented out, when I run this cell, before you run it, you can predict what's going to happen. And we get a name not defined, and that's because this was commented out, therefore the value was never created, the variable was never created in the value set. Okay, so that's comments and how we should be thinking about comments. And remember, comments are a communication to yourself and others about the code that you're writing, and they're an incredibly important part of writing code. Really quickly, a comment that's wrong is also a bug, right? Because if I see a comment that's wrong and I see a line of code and it differs from the comment, I don't know which is right, and therefore there's a bug, and one of those is wrong. Okay. Any questions about comments or variables before we move on today?
I have a question. I mean, maybe I shouldn't be asking since I'm a co-CHack master, but I'm just wondering, you were talking about, the precision of your numbers. So how is your zero defined? Like when you're looking at differences between numbers, does that become an issue as well?
You mean like in the case of, let me scroll back up here. In the case of, how is that number defined?
Well, I guess what I mean is, let's say you had like single respect to double precision, right? So in one case, like your single precision 0 might not be a 0 in double precision. Right?
Ah, yes, right. Great point. So, there are, just like there are different representations between an integer 0 and 0.0, those are actually represented very differently inside the computer. The way we represent 0.0 could actually be different depending on how many decimal places are there in the computer. And so I think that's what you're getting at, is that there are really, really long numbers with lots of significant digits actually have an even different representation. And it's important to think a little bit about as you begin to write code that sometimes you need all those digits of precision. Sometimes you don't. So thank you. And that's right. So it looks like there's some issues with folks unmuting themselves. Does it matter in terms of good or bad style how long comments are? Generally, no. So I have some strong opinions about this, by the way. So generally, no, it does not matter. Jesse had a great comment yesterday, is if your comments are that you're writing are longer than your code, you're probably over commenting. And if you're doing something that tricky in one line of code that needs to have 5 lines of comment, you probably shouldn't be doing that in that one line of code. You should probably doing it in more lines so that it's more readable. So I wouldn't say that comment length is necessarily an indicator of comment quality. But I believe if you're writing alongside folks that use English as their primary language, then the comments should be written in English. It's a good idea to try to write in full sentences, if for no other reason than when I try to write a shopping list, it's usually unintelligible to anybody but me. And the same is true of comments. If I try to write them really fast, then if I come back later, they may not make any sense. So a full sentence comment, again, written clearly in English is probably the best kind of comment. Yeah, so there's a great hot take in there from co-C Hackmaster Wes, which is that comments should explain your thinking, not describe what the Python is doing. The code itself should describe what the Python is doing, and the comments should, I think that's a great take, should be to describe sort of the big picture of what's going on. Okay, so great questions and comments. Thank you very much. All right, so let's get to the new stuff for today. And I want to start out with data structures. And one of the things I love about computing is that there's so many cool words like flow control and data structures, cool phrases. But what they actually mean is relatively straightforward and simple. And so a data structure or a data type, let's start with a data type. So we've already seen data types thus far. These are the integers, the strings, the floating point values. Those are data types, right? They define how the data are stored in the computer's memory. A data structure is something that holds data types. So a data structure usually holds more than one piece of data, or more than one datum, we should say. It typically holds multiple pieces of data. The two ones that I want to start out with today, because they're so critical and important to the structure of Python, are lists and dictionaries. So let's move right on to lists. And the reason that a list is a data structure is because it will hold multiple variables or values in, they can even be in different data types. So let's start with this, this example here. This is how we create a list. So we have a variable called myList, and we assign to it a list of 3 things. We start out, the way you define a list is that you use the square brackets, and those square brackets are really important here. And then it contains 3 components, 3 strings. The data type of these 3 objects are strings. And we can tell that because it has quotes around it, in this case, single quotes. And so we can create a myList here that is a data structure, a list data structure containing 3 values. I is one, like is the second one, and pi is the third. Okay, so that's a list. And the critical things that we should walk away from at this point in knowing is that you denote a list by brackets, the square brackets, and then we can put some comma separated values in there. We can actually use variables to define those values in there, and I'll talk about that in a minute. Another important thing I want to mention about lists is that they're an ordered collection. And so again, by collection, I mean it's a data structure that holds multiple pieces of data. And by ordered, I mean that the order they go into that list is the order that they can be referenced or come out of that list. And so if we look here, I have an order, right? I have I like pi, and the ordering is important there because that's a full sentence when I display it like that. And the other, and so you can kind of think that each element in a list has an index in the way that your home has an address on your street. You know, so your number 10 Downing Street or whatever, I think that's where the prime minister lives. But so there's a number that references that house on that street. And in the same way, there's a number that references an individual value in a list because a list is ordered, so they appear in a specific order. And so let's think about that in a second. And that means that because we're using Python, and Python begins its numbering as 0, which is actually most programming, many computer languages begin their numbering at 0. There are a few exceptions, like R and MATLAB and Fortran, I believe. But in Python, numbers, like ordering things starts at 0. So the index of 0 is the value I, and index of 1 is like, and 2 is pi, and so forth. And we can actually use these index values to pull back certain values of your list. And so, for example, if we wanted to see what the first object in our list was, remember the 0th element, we could reference it by putting brackets after the variable name and then the index, in this case 0, in between the brackets. And again, so if you've had sort of MATLAB experience, this is probably somewhat familiar. But again, MATLAB starts counting it at 1 and not 0. And so here, you know, you should take a moment to try to think about what some of these cells will result before you execute them. That's always a good sort of way to, you know, build your skills, is by sort of predicting what you're going to see. But I think, you know, most of us will think they see this and it should be I, right? So let's try that. And in fact, what I do is I return the 0th element, that is index of 0. And that happens to be the string. Remember, string is the data type I, right? Okay. Sometimes you want to try to, you know, access individual components other than just the 0. And so you would put in the index. And here, if I try to index 3, maybe forgetting that it starts at 0 and I only have 3 words in my list, I try to access the 4th element, the one off the end of the list, and I get an error, right? Because I've tried to access something off the end of the list. And so the index error actually tells us something informative. It says the list index is out of range, with the range being 0 to 2 inclusive, right? So 0 I could do, 1 I could do, 2 I could do, but 3 I cannot because it's off the end of the array. Okay, so one of the things that's good to get familiar doing is actually searching when you see an error like this. And Colab has a really nice feature where it's letting me right now jump right over to Stack Overflow. I'm not going to do that at this moment, but this is a great way if you're debugging code in a notebook and this stack trace, that's what this is called here, this trace back of the error isn't easy to understand. You can click this button and go to Stack Overflow. And Stack Overflow is like, I don't know, answers.com or something for code, and it's a great place to look for help. Okay. One of the nice things is that you can change values in a list relatively easily. And so here I'm trying to set my 3rd element in my list, which has an index of 2. And instead of thinking that I like pie, I want to say I like cake. So I can set that 3rd element to cake, sorry. Yeah, that 3rd element to cake instead of pie. So if I do that and then ask for my list, I've now changed the representation. Now, notice the order is the same. All I have done is swapped out a particular value in that list. Okay, and you know, I can do this as many times as I want, and I can edit all the different components of a list. And I do not like toenails. I would much rather prefer pie or cake. Were I going to eat something? Were I going to eat something? So. The other thing that you may want to do, this is actually a really common pattern, is to create an empty list and add things to it. So let's talk about that really quickly. If I do this, I've now created an empty list. And the reason that you can see that it's empty, well, one, when I execute the cell, nothing comes out after it. And I can make that a little bit clearer here by doing that. Because remember what Jupyter Notebooks and Colab does is it displays the value of the last element in the cell. And so here you can see it's an empty list. And again, we specify a list. If I scroll up here, the way you specify a list when you set it, apologies, here is that I put the elements in a comma separated between brackets. So if I put the elements in comma separated, if I put no elements with no commas between two brackets, that's an empty list. And so that's exactly what we've done right here is we've created an empty list and we've put it in the variable a new list. And so when I put it on the last line, I can see that it returns nothing. Now, again, this is a common pattern. We start out with an empty list and we want to start appending things to them. And so here we have to use what's called a function. And you've already used a number of functions, but maybe you didn't know it yet. But we're going to use the function append. And this is what we do is we use the variable name. And then technically this is called a method, not a function. But I'm going to call them the same thing. And so here we have our list, our new list that happens to be empty. And then on that list, I'm calling the function append. And then I'm appending an element, which is a string first element, okay? And then I'm going to print out the list, and then I will append a second element to that list, and then print out the list. And so if we, again, try to do that thought experiment where we predict what the cell is going to output, you might think that it's going to output a list with brackets that says first element in the list, so there's one element, and then it prints it out again with brackets, and it's a string that says first element in the list, comma, second element in the list. So let's test that hypothesis by executing the cell. And so this output here is from our first print statement, right, where we're printing out the list with just the one element appended. And then here's where we add it, and then this print statement here yields this output. So there was a question, why would we want to do this rather than just writing your list in one line of code? Okay, so it's a great question. And let's say that I have a piece of software and it's connected to some visual recognition system and it's watching people play basketball. And I don't know why I chose basketball. I don't play basketball, but you have some piece of software that's watching people play basketball and it can see when the ball leaves somebody's hands, right? And what you really want your code to do is not count every time it leaves somebody's hands to a pass, but when it leaves somebody's hands for a shot on basket, because your goal is to calculate how many times people took shots on the basket, right? And so if your list, you don't know at the start of the program how many times you observe the ball leaving somebody's hands to go into the basket, right? But so your code is monitoring the camera, and each time it sees the ball leave somebody's hand, it thinks, okay, I might add this to my list, but then if it goes to another player, it doesn't add it to the list. It only adds it to the list when the shot goes towards the backboard. So that's a typical use case where you're collecting up observations of something as the code is running. And so you need to be able to dynamically add things to the end of the list. So most lists actually are like this, where they're not defined necessarily like I did somewhere up here, where in fact they're created as empty lists and then you append things to them as the program runs, as things are observed or as events happen. I hope I answered your question with that.
Makes sense, thank you.
Yep. Okay, so, okay, great. New list is, append is not the only thing that's available for you to do functions that you can apply to a list. There's quite a large number of them. In fact, we've already seen one and we've been using it implicitly and haven't really thought much about it, which is the print statement. And actually what we're doing with print function and what we're doing there is we're actually calling that on the list, and there's some code written in Python that knows how to convert that to a string, right? And we can look at a quick list of other functions that you can apply to lists. So here's append, and that's the one that we've already talked about. Let's talk about insert really quickly, which is the idea that instead of appending to the end of the list, I might want to insert an element somewhere in the list, right? So here is the element, the way we would read this, and reading through this will tell me a little bit more. But if here is the thing that I want to insert, so the set, third element or first element or the shot on the basketball court, and this index here tells us where we want to insert. So this value here, a.insert 0, with the x being the thing we want to insert, would put it at the front of the list, right? Whereas this one that we haven't really talked about what's going on with len, and I'll get there, but this returns the length of the list. And here we're saying, insert this value x at the end of the list. And so this form of insert is actually identical to append, right? They do the same thing, because I'm trying to put the value x at the end of the list. So there's a bunch more things here. There's clear, which, as you might imagine, removes all elements to the list. And I'll let you go through this in your own time. The important thing to get out of this is, one is append is a thing that you can use on functions. But the other thing that's important to recognize is that there are many more functions that operate on lists, and we won't have time to talk about them all. All right, let's dive into len a little bit more. So len is short for length, and it works like print in that I can pass it a list and it will do a calculation for me. And in this case, it's going to return the length of my list. And remember, this is 2, not 3, because a new list is the one that we created right here, and it has 2 elements, first element and second element. All right, let's say, do you remember this? What would this output? Well, if you remember, we had this have 3 things in it, right? So then I would expect this to output 3, and that's in fact what we get. So as you can see, length outputs the length of the list. So we've talked about how to address elements in a list, how to change elements in a list, how to append elements in the list, and the fact that there are many other functions that you can run on a list. So before I move on, it looks like there have been some great questions in chat that have already been answered, but I just want to take a moment and see if anybody has any questions that they have about what we've covered thus far.
Oh, I have a quick question.
Yeah.
So when you showed all the other command types similar to append, like insert or extend, I remember that there's a difference between append and extend, but they act really similarly. Would you mind explaining the difference?
So, yeah, I will put it. Let's see. Let's do a. I think I can come up with a quick demo for this. So, oh no, I hit escape too many times. Oh, this is really going to drive me nuts. All right, so let's create a temp list that just has 1, 2, 3, 4, right? And then let's create another list called B temp list. All right, and then if we do a underscore temp underscore list dot extend.
I would say in the pickle theme, we could call one sauerkraut, something like that.
And let's print this out so we have it at the end so you can see what's happening here. So what extend has done is essentially concatenate these 2 lists. And so this concept of iterable here is a bigger concept than I really want to get into. But you can think of an iterable as any data structure in Python where you can iterate over the components, where you can go one by one by one by one through the components. And so in this example, extend is basically combining these 2 lists, which, for giggles here, let's do the extend is basically like using the addition operator on 2 lists, which concatenates those 2 lists. So I think more often than I see extend in code, I see people using plus because it's a little bit more Pythonic, meaning it's a little bit more intuitive. And I just want to make the point here that remember, we set A to 1 through 4, and then we extended it, right? Which changed the value of temp lists to include 1 through 8. So that down here, the list that we were operating on was that extended list, not the initial list. So I just want to be clear about what we're seeing here. So again, I usually, when I'm trying to concatenate two lists like that, I will usually use a plus. Extend has some other features like being able to take a dictionary and a list and put them together that is beyond the scope of what I want to cover here. But that was a great question. Thank you. Okay, great. So slicing, again, we have some cool words in computing, don't we? So now I want to slice up a list. And what this is like doing is saying, take a list and give me pieces out of that list. So I don't want just one element, which is what we do when we address with the brackets and a single number. Now I want a range of elements from that list. And so in this example, I'm going to pull out my list. Now there's something really important that I want to mention here, is that when you see slices, and the slice is denoted by the fact that there's a, can't believe I can't remember if this is a colon or a semicolon, whatever. The two dots, okay? When you see the two dots between two numbers in square brackets, that's called a slice. And what we're doing is we're telling Python, we want to slice out the elements of this list, starting at not the first element in the list, which would be 0, but the second element in the list. I want to start at the second element in the list. And here you see 3. Now, if you recall up top, not here, but let's see. Oh, I'm getting better at this, which means everybody can get better at this. If you remember, my list has 3 elements. And the other thing about my list is that, remember, when I did that, I got an error, right? I got the list index out of range, because the valid indexes for this list with 3 items are 0, 1, and 2. So here I'm asking for a slice that goes from 1, right? That means that would be like, and then 2, and then 3. But 3 is off the end of the list. So you might think this would give you an error if I ran this. But in fact, it just gave me the last 2 values. And the reason is that that upper bound in a slice is called non-inclusive. And technically, this is a thing called a half-open interval, where the bottom half is inclusive, meaning we've asked for the element of index 1, but the upper end is exclusive. So it'll go every number up until, but not including 3, which expands to 1 and 2, right? So if that didn't make sense and there was a lot of gobbledygook, when you slice, just remember it should always be 1 plus the last index that you actually want, because it's non-inclusive. And so that's why when we slice this out like this, we get the second element in the list, which has index 1, the third element in the list, which has index 2, but we stop there because the third element is non-inclusive, right? Or the third value is non-inclusive. Apparently I like giggles because I talk about giggles a lot. So yeah, let's see what would happen if I asked for just 1 and 2. And again, remember that 2 is non-inclusive. So I'm asking for the second element in the list, which has index 1, and then I'm asking for everything below 2, which is what? It's really only 1, right? So when I do this, I get a list with 1 element, right? Because if I go counting from 1 upwards and don't include the 2, I stop counting at 1. Okay, so that can be a little hairy. So let's take a break and see if there's any questions about the concept of slicing and how that upper bound works. Okay. Tried having it go to 4 and it worked. So you tried this and it worked. And that seems a little counterintuitive, but the slicing is smart enough to kind of ignore the index error. And so we don't get an error when we slice off the end of the list. It would be fun to actually, well, for me, it would be fun to actually think back about, why that design decision with the language. It's a nice safety guard in that it reduces the number of failure modes that you can have when you're slicing. But it's important to kind of think about what the upper bound is going to be. So thank you for asking that. That was a nice demonstration. Let's see. All right. And actually, this is probably related to why that design decision works, where I can ask for a number larger than the last index, and it doesn't puke or throw an error. And that's because the upper bound of slicing, you can actually leave that off. And so if I did this example here, I can get that missing upper bound basically means everything else in that list, right? And so it's a nice way if you don't know the length of the list or the length of your list is changing, and you just want from one point on to the end of the list, this is a really nice way to pull back just those components that you want, is to leave that upper bound empty. Okay. What's neat about slicing is that in addition to being able to pull the values out, you can actually set things based on a slice. And so remember earlier, I was able to set, like I had a 0 in, or I had a 2 in here, and I changed, what was it, cake to pie or pie to cake. It's hard for me to remember because I love them both so much. But here, what I can actually do is I can slice out the part that I want and then change multiple components at once, which I think is pretty hot diggity cool. So let's do that. And so remember up here, my list last time I looked at it was, what was it? I like toenails, right? And so here we changed all in one fell swoop. We changed like to love, and we changed toenails to puppies, which is much more in line with the way I think about the world around me. So slicing offers a lot of cool things that in terms of like list retrieval, but also in terms of list modification. And you'll see it a lot of the place, and that's kind of like that's pretty common in Python. So I talked about how the upper bound can be missing, and you'll let that kind of fill in. The lower bound can be missing as well, and so here I can just have the lower bound missing, and it'll pull everything up to my 1 minus that index. So remember, this starts at 0, so there's our 0, and then here's our 1, and I don't return 2. Why? Because the upper bound in slices is always non-inclusive. So there's 0 and 1. Okay, so that's slicing. And I'm not ignoring the chat. I just see that Stephanie's doing an awesome job of covering a lot of things. A couple things I just want to just speak out loud is that I've created these lists right now using very simple data types. So the list contains base data types like strings and numbers and floating points. But lists can contain other lists. In fact, a list can contain any object in it that exists in Python. So I could have lists of lists of lists. Things start to get kind of disordered and confusing at that point. And generally, when you have a data structure that's complex, you start to move towards things called objects. We don't have time to get into that. You can take a whole class on object-oriented programming here at UW, but generally speaking, when data structures that you're making on your own by doing lists of lists start to get complex, that's when you might want to start thinking about organizing them differently. Okay, cool. I think the other thing I want to talk about here is negative indexing. And this is something that I think this is pretty unique to Python. There are a small number of other languages that do it. And it's worth noting here, although you probably won't need to do it in your projects, but essentially that negative indexing, so if we have, I don't know if my video is reversed for you or not. So if we if we have a list and we're going from left to right, hopefully that's the same on your screen, and we count 0, 1, 2, Sometimes we want to go from right to left and count down. And so you might want to say, well, can I do -0? And the answer is no, because that concept doesn't exist. And so if we want to start counting from the end of the list forward, the first element in the list going in reverse is -1. So it's not -0, which might be intuitive, but it's -1. And so let's actually do that out. And again, you should guess what this is going to do, or try to think through what this is going to do first. And I think it's going to say something about puppies, because I love puppies. And sure enough, it does, because remember, we're going from the end of the list forward. And so -2 would be love, and so forth. And just like with positive indexes, we can use negative indexes to slice. In that case, because, so notice up here, this is not a slice, right? This is directly addressing that element. Whereas in this case, I'm slicing it. And so now the upper bound of -1 actually has a different meaning. At this point, it's non-inclusive. So this would put out -3, -2. And then because it doesn't include the -1, we don't see puppies, right? If I wanted to see puppies, I could do -3 and then let the upper bound be open, because remember, that means the whole rest of the list. And then this would just give me I love puppies. Okay.
Dave, can you slice backwards?
Can you slice backwards? So you mean like something like that?
Yeah, exactly.
Yeah. So you totally can slice backwards. Trying to think about, let's see. Why am I getting an empty list here? Yeah, so you can. I have to think about what's a good way to demonstrate this, given our list here. Let's see.
You're talking about reversing order?
Yeah, thank you, Wes.
Can do, yep.
There we go. Okay, so yeah, I'll let you look up why the double colon is reverse slicing. Okay, so as we were talking about earlier, lists can contain anything, and they can contain anything all at once. And so here I've got an integer, a string, another string, and then a floating point number. And my list will happily take all of those elements. And so that's pretty sweet, that we can combine all these things. Similarly, you can create lists of lists. And so this, I know that there's been some discussion of this in chat. And so when we start accessing elements, so this is our first element in our list of lists, and it happens to be a list itself. So when I print out the 0th index, or the first element in our list, I see this row, which corresponds to up there. And so you could imagine if I printed out, if I did that, I would get A, B, C, D, right? So let's go, I'm gonna change this back so that it reads 0. Okay, so there's my first row. You can kind of think of these as rows, and I'm sort of building up a matrix, right? For those of you who are sort of thinking about it like this. And then when I do this, I get a list. And then if I ask for the second element, that is index 1 in this list, what'll I get back? And again, try to guess before you run the code cell. But I should get back 43. And that makes sense, because this part returns a list. And then when I ask for the index into that list, I get 0, 1, which is 43. Okay, this is kind of meta here, people. So let's just let that sink in for a second. And I'll use a separate example of this. In this case, I'm asking for the second element in our list up here, what happens to be another list. And then when I ask for the second element in that list, I get B. And so it is possible through primitive means like this to create matrices. And I will tell you right now that while this works, and it's a great place to get started and wrap your head around data structures, it's not very performant relative to things like NumPy arrays. And so I think later we'll be talking more about NumPy arrays, but there are faster ways to represent data, like I said, but these are great ways to create your own basic data structures. And then finally, I can pull out that whole list here, because doing this that I've done here, right, is equivalent to doing something like this, but without actually naming a variable. Because what I've done here is this component here gets assigned to the variable a list, and then what I'm doing here is like taking out that component up here. So this is actually shorthand for something like this, and it avoids the instantiation and naming of a temporary variable, but they're totally equivalent. And it's up to you how you would write that code. We can have some vigorous arguments about which is more clear to somebody coming along after you. But the important thing to understand here is that these are both equivalent and they return the same value. Okay. So that was slicing, the ability to pull out pieces of a list or set pieces of a list. That was negative indexes, that is moving backwards through the list. And that was the idea that lists can contain almost anything. In fact, I'm not aware of anything you can't shove into a list. I would love it if somebody told me, I mean, you can't shove a reserved word in a list, for example. Well, you can, some of them, but for the most part, not. All right. So that's lists. Let's move on to dictionaries, unless there's any questions about lists. All right, great. All right, so dictionaries, yes, they're more than just reading on a Friday night, because I know that's what you all do on a Friday night. Sometimes you want to be able to access elements that are stored in a data structure, not by their indexes like 0, 1, 2, 3, but instead by something that conveys more information to the reader, or is somehow a key or a reference to a particular data in a collection. And so you can think about a dictionary on the internet, right? So we could go here and we put in, so I'm going to go to dictionary.com. Oh, come on, internet. So Google's doing the right thing and trying to protect me from hurting myself. Oh, well, if I go to like dictionary.com, look, I've apparently already been there. And I put in the word pickles. I want to go and get all the, wow, look at that. Apparently dictionary.com and Dave Beck think alike about the meaning of pickles. But you know, somewhere in the back end of dictionary.com is a large dictionary, and I put in a word and it goes and retrieves the value associated with that word. I put in a key and I get the value back. And that's exactly what a dictionary does in Python, is it essentially allows you to access elements based on a key. And it's pretty convenient because a lot of times we can use strings as that key. And so unlike lists that use square brackets when they're created, dictionaries use these curly braces. And so this line here would create an empty dictionary, as my comment lets you know. And then what this would do is set the value of the dictionary key pickles to a cucumber preserved in vinegar or brine. So if we run the cell, we see a dictionary comes out, and it's got one element in it, which is called pickles. And there's our key and there's our value. So a dictionary is really made up of key and value pairs, in the same way that, you know, dictionary.com is made up of word and definition pairs. So let's see. The other thing I want to point out here is, remember when we printed a list, right? It used square brackets around the element of a list. Well, in this case, it's using the curly braces. And so that's the trigger to us to think, oh, that's a dictionary, not a list. The other thing that you can see here is the key, the word pickles, is separated from its value by the colon. That was the colon, right? Okay, by the colon. So that's, again, these are triggers for us to understand the difference between a list and a dictionary. One interesting thing about this is that we can access the elements in the same way that we could as a list, where except instead of using, actually, let me create an additional example here. Instead of using an index to access the definition of pickles, here I use the key, right? So this is pretty cool. Again, now I don't have to worry about 0, 1s, and 2s. I can use things that mean something to me as a reader and a code writer. Just like if I try to access an element that's off the end of a list, if I try to access an entity that's not in my dictionary, I will get an error. And instead of being an index error, this is a key error. And what that's telling me is that that key, the word pickles with a capital P, doesn't exist in my dictionary. And so that's another thing I just want to emphasize here is that this is different from this because these are two totally different strings in Python, right? The fact that we would pronounce them and say them the same way is irrelevant. The important thing is that there's a different capitalization in there. So again, if you try to access something that's not an existing key in the dictionary, you'll get a key error telling us that pickles is not in our dictionary. Okay, like lists, we can reassign values. So if you remember before, I had I like pie, and then I changed it to I like cake. Well, now I can change the definition of pickles to actually have something about the size of the pickles. And so my favorite kind of pickles are the relatively small ones. And so here, maybe I want to change the value of a pickle to reflect the fact that in my mind, pickles tend to be small and not large. That's not true. Pickles can be quite large. But anyway, I do like pickles as well, in case anybody's wondering. So now we have a dictionary and we can set values for it. We can change values for it. We know what happens if we try to access something that doesn't exist in it. Let's add 2 more key value pairs to them. Let's do the list, because remember, a list is an ordered collection, and so the ordering matters. We can also use append. So actually, we can't use append, but I just want to show you that where there's dictionaries, there are a whole bunch of other things that you can do, like you can remove elements from your dictionary, you can sort elements, you can do lots of things with your dictionaries. And I feel free to play around with dictionaries. There's a lot of great things that you can do with them. Yeah, I guess I'm not going to add the word dictionary to this. I guess I could. Here, let's do that right now. So my dictionary equals a collection with unique indices. Let's say keys. Okay. And so now I've got 3 things. Oh, something else I want to show you. So remember when I described how you can tell if a dictionary is a dictionary, because it has the curly braces, and then it has the key separated from the value by the double dots here. What you can see is that each element, or this is like one key value pair, and then there's a comma, and there's my next key value pair, and then a comma, and my next key value pair. And so this is, if I wanted to initialize a dictionary, I could take something like this and set it to the value of a variable, and I would have sort of a pre-made dictionary to use. All right, so we've covered some really fun data structures. I do want you to remember here that when we have lists, the items are ordered, and we typically access them by their indexes that start at 0. When we're slicing a list, the upper bound of a slice is non-inclusive. So we would always subtract 1, and that'll be the last element that appears in our slice. We can change the values of variables. We can change the values of elements in a list. We can even change the values of elements in a list through slicing. The difference between lists and dictionaries is that dictionaries give us a way to access elements in a data structure in a collection using a name or some unique value. It doesn't have to be a string. It could be a number, which makes it be more like a list. It could be a floating point number. So it can be a number of different things that are my keys. And the values themselves can be a number of things. So in a dictionary, the values could be another dictionary, another list, or other kinds of components. And so, like I said, you can build up very complex data structures with lists and dictionaries. Any questions on this before we really change gears and get into flow control, which is something entirely different? Nope. Nailed it. All right, let's move on. Okay, so flow control is really a fancy way of saying that you want to change maybe the order of operations, so the order of statements that get executed, or not execute certain statements, or execute the same statement over and over and over again. And if you think of the state of your Python interpreter as sort of moving through your code, right? If you had your code all laid out and you had a little arrow that was pointing to which line was executing now, flow control allows you to do things like be at this point and then jump over to this one, or be it here and then come back and do these statements again, right? Do things over and over. And so flow control is really how you get almost all of the sophistication from programs out there, is the ability to be able to change what, where the sort of the interpreter is looking in your code at any one time. And it generally falls into three components here. I would call this, let's ignore selection, iterated, and sequence, and let's call this if. So this is an if statement. So I test some condition like if Dave likes pickles, then go and execute these statements. If Dave doesn't like pickles, go and execute these statements. And then when both sides of this, depending on which way the flow has resolved, they unite and come back together after the if. So if I don't like pickles, sorry, that's this side. If I don't like pickles, then the code, it runs this part and then resumes executing here. So that's the high level concept of an if statement. And in a loop, we might do something where we come in and say, if I'm done looking at all of the basketball shots that I've recorded, then go on and keep doing something else. But if there's more basketball shots that I need to do something with, like calculate how far the player was from the basket, then make that calculation and go back up. Are there more basketball shots for me to look at? Then yes, make that calculation and go up. And so this is the idea of a loop where I'm running certain statements over and over and over again. And then sometimes you want to have blocks of code, like a function that you execute repeatedly, or that you execute this block and then that block and that block. And that's functions, and that's what we'll talk about at the beginning of tomorrow. Okay, so again, selection up here refers to the idea of an if statement, and iteration up here refers to the idea of loops or repeating something over and over. All right, so let's use our understanding of lists to kind of work through how if statements and loops work. So we begin by creating a list of instructors. And so this has 1, 2, 3, 4, 5 elements in it. If I run this cell, I now have my instructors variable holds a list with 5 strings, right? Let's do a really basic if. So Python has a really cool way of letting us look inside of a list and see if something exists there. And basically, we can ask Python if some element is in a list, right? And what I love about Python and why it's, of all the languages I know, my favorite and why I love to teach it is that well-written Python can read like English. In fact, I can read this out loud to you. If hacker in instructors, right? I mean, I might want to see the word is in there to be grammatically correct, but that reads like what our intent is with the code, right? So what I'm saying is, if the word hacker appears in the list instructors, then do something. And hacker is not a name like Dave, Jesse, Wes, and Stephanie. In fact, hacker looks like it's not a real instructor. So when we encounter this condition, when this evaluates to true, in other words, when hacker is found in the list of instructors, print out fake instructor. And so we see hacker up here. And so if you think about what this cell is going to do before you run it, you might think it's going to. Anyone? let's say it's going to print fake instructor, right? So that's the fundamental concept of a list. Now, there's a lot of stuff that can go in here. We used a really interesting simple case of, this really nice in operator that allows us to look to see if something exists inside of a list. But there are lots and lots and lots of other ways to do it. I want to point out here that the word in is a reserved word. And so you can't use it as a variable name. And in fact, if you look at the coloring that Colab and Jupyter is using for these here, and I don't love these colors, but there's magenta and there's kind of a blue. You can see that the interpreter, or the Jupyter or Colab is actually trying to color code things to give us a little hint about what they are. And so it's coloring strings as red, the if statement as purple, this in reserved word as blue, and a variable as black, and then, I don't know, what is that, tan, for functions. And so, you should let your eye be drawn to these hints, because they'll tell you something about the nature of the code that you're reading. Okay, so in's a reserved word. Another reserved word that we talked about before is true. And what this means is the value true. So, there's sort of a special value in Python to represent true. And as you might guess, there's one that is intended to represent the value of false, meaning some statement evaluates to true or false. And I meant to type true, but false is false, and that is true, right? False is false. But false is not true, right? Okay. Just cogitate on that for a second while I look at chat. Great question. All right. So the question was, what would happen if I didn't have the indentation, right? If I did this. I'll show you and then I'll explain it. So when you have statements that have a dependency, in other words, the outcome of this, the outcome, whether or not this should be run is dependent upon this statement. What Python does when it sees this double dot is it wants to see the next block of code be indented, because this statement here is part of this if block. I'm using the lingo from Python. So this is called a code block, and this if statement is attached to this print. And so if I didn't have the indentation, this print is no longer attached to the if statement. And it says, wait, you have an if. I expected to see an indexed block of code telling me what to do, but you don't have anything there, right? And let me demonstrate this just a little bit more. If I do print, okay, we see this gets run because it's inside the if block. And then here, this also gets run, but notice it's outside the if block, right? So if I then were to, let's see, what's a good way to do it? If I were to change this and remove this dash, for example, right? So now the C hacker with the dash doesn't actually exist in instructors. It doesn't run this, the fake instructor, but this print puppies line is in a different block. It's not in a block, actually, because it's not indented. It's not part of the if block. So that was a fantastic question, and let's just review that again. When we have a code block, like an if, or some of the loops we'll talk about later, we need to see the associated code, the things that should be run when this condition is true, inside of an indent, right? And so just because these lines follow each other, they are unentangled because this one is not indented. My preference when I'm writing code like this is to actually put a blank line in there so that I've delineated this code block from this statement. And so it's clear what my intention is. But that's a great question. If you don't have that there, you won't get the result that you expect. And here I'd see no output. And then when I put the dash back in, because that word is up here with the dash in there, I see the output I expect. Okay, so that's a great question. it's a nice setup for some of the next things I'm going to talk about. But yeah, this indentation of code blocks is something that's actually really, really important. And yes, you can have lots of things in here. I can have, right? And so it executes this first line, and then because we're still in the same code block, it executes the second line. Okay, so I can have any number of statements I want inside of a code block. So great question. All right. All right, so we talked about in being a reserved word, and we talk about how this evaluates to true. Sometimes you want to actually handle the other case, and let's come back up here. In this example, what we did so far is we created an if statement that said, if chacker is in the list of instructors, then execute this part. But we never handled the case when it's not in the list of instructors, right? So what happens when there's no chacker in our list of instructors? Well, then we can use the else. And that's how we balance an if, meaning we do something when it's true, and then we have something to do when it's false. We balance it. Okay, so let's do this kind of quickly here. I can see that there are fake names in my instructor list, but if I swap this out, and let's just remove the dash again, because we did that before, and that's pretty straightforward. Again, what's your intuition about what it's going to do? Well, since that is no longer true, it won't execute this side, which means it'll skip over to the other half of the if, the balanced out, and then it'll print the other statement, right? So what we've got here with the if else is a balanced if statement. And it's super important that you make every attempt to balance your if statements. And there's a lot of great theory behind this, but it's pretty well known that unbalanced if statements, that is when you handle the true case and you don't handle the false case explicitly, is the origin of a lot of bugs. So because what happens is you think, oh, I handled the true, but then you don't think about, well, there was something that I needed to do when that statement wasn't true, right? Which is, print out an error or do something else. And if you haven't balanced your if, you haven't actually taken care of that. So always try to balance your if. Sometimes there really is no action to be taken. So in this case, we look to see if Wes is in the list of instructors, and if he is, we do something. But if he's not, we just don't want to print out anything. We just kind of want to move on. But we still want to balance our if because we're good citizens. And so we can use this concept of pass, which is basically like do nothing. So when the code is running, it comes down here and it looks to see if Wes is in our list of instructors, and in fact it is. And then it prints this out. But let's say Wes wasn't in our list of instructors. So this evaluates to false. And so it does not execute this. It comes over here and it sees an else. And then it says, well, this is what I do when the statement is pop false. And it says pass, which means, again, do nothing, in which case we've balanced our if and we get the expected output. There is no difference between these two. They're totally identical. But as a good citizen and somebody who wants to help the readers who come after you and avoid bugs, I always recommend putting in the else and the pass if there really is no action to be taken on the negative side of the if. Okay. Min and max aren't reserved words. So there was a question in chat about assigning min and max. So actually min and max are not reserved words. LEN, remember len tells us how long a list is. It's really tempting to want to calculate the value, the length of something, and then put that in a variable named len. But if you do that, you'll clobber the function length, you'll clobber the function len, and then all your code will be broken. So while they may not be reserved words, you really want to stay away from using them as variable names and function names. I can think of some pretty cruel things to do to people by overwriting those. All right, we'll talk about that some other time. Okay. Right. I'm not gonna talk about the difference between single quotes and double quotes because I want to move along. But suffice it to say that for the most part, they're completely compatible, or you can swap one out for the other. In this instance, I need to use the double quote in my string. because I have a single quote that I want to encapsulate in this string. So this is probably the single most common reason that you would decide to use double quotes over single quotes, is because the string you're trying to use already encapsulates one of the other types of strings. All right, so let's just move along through that. Okay, sometimes you want to test more than one thing in one if statement. And so here I have a variable my favorite, and I've set it to pi, and then I want to check it. And if it equals cake, I want to print out something. And then I want to also say, well, it could be pie. So if it's not cake, if it's pie, do something else. And then I have my last thing, my conditional fall through, which is, hey, it's something else entirely, right? And so if I run this with my favorite set to pi, it prints out this statement, right? If I change this to cake, sorry, it prints out this statement, right? That's important. I want to, here, let me go back and run this again so that oh, no, wow, that's not what I wanted to do. Although the idea of a pie cake is getting me very excited right now.
I think you just invented something.
I think so, yeah. I'm gonna go and start after this and start baking. Okay, so when it's set to pi, it doesn't, so this evaluates to false, right? So it doesn't execute this one. And then over here, this evaluates to true, so it would execute this one. And I can actually have any number of elif, which stands for else if. I can have any number of these all stacked up in here. There are probably better ways to do that than a whole chain of if and else ifs, but that would certainly work. And so this allows me to sequentially evaluate a particular set of values for, in this case, my favorite. And then when I hit this case where I had this pie cake, which just is making me very excited now. So this evaluates to false when this is pie cake, so this doesn't run. This evaluates to false when this is pie cake, so it doesn't run. But when this is pie cake, the else is the catch-all, and so this statement will run, and that's how we get this last output. Okay. Let me make one more point before I stop for questions, and that's, if you can see, these two things right here are not the same. So let me set this back to pi. Okay. So here I've got if my favorite is cake, else if my favorite is pie, and then else. And here I have if my favorite is cake, and then I have if my favorite is pie. And these two are not equivalent. And I really want to stress that, because in this case, this statement only ever gets evaluated if this one is false, right? But imagine a contrived case where this happened to be true and this happened to be true, then this would run and this one would run. So I really want to emphasize the difference between these two. This is one if statement that gets resolved, and then, excuse me, this is a totally separate statement that gets evaluated. So they're not chained together at all, and they have wildly different consequences. So I really want you to think a lot when you have multiple if statements in a row, testing, say, the value of a variable. Should I be using an if else here or an elif? Okay. And I guess, yeah, so there are other reserved words, and, or not. So I can say if my favorite is cake or my favorite is pie, which again is different than having two ifs afterwards, right? I'm saying if this is true or this evaluates to true, then run this, right? And we can do that right now and see that this second half of this statement evaluated to true, therefore the whole thing evaluated to true. I could do and, which wouldn't make any sense because the value of my variable can only be one thing at a time, but I can run that as and, in which case it can never be both pie and cake at the same time. Therefore, I get an else that prints this. Although with my new pie cake, it could be both pie and cake at the same time. We'll have to see. Okay. So you have and, or, and not, and you can create really complex chains of Boolean expressions to test lots of very complex things at once. Okay, it looks like there's been wonderful efforts to answer questions in the chat, and I thank you for that. I will break here for 1 minute before we get into 4, because I do want to make sure that we have a little bit of time in the breakout rooms, but I want to just stop and make sure there are no questions about if statements as our flow control. Okay, I'm gonna move on. These are questions that I have opinions about and I want to answer, but they're about the elusive cake pie, so I will skip over it for now. All right, so our basic iterator that we're going to use is a for loop, and the sort of canonical example of that is looping over items in a list. And so if we look at this thing here, we have for item in list. By the way, this is not valid code. This is a what we call pseudocode. And by pseudocode, we mean it doesn't run, but it's even more like human language, right? And so, you know, what I want to do in this is I want to, for each item in the list, I want to do something with that item, right? So if I had, well, let's use this example here. Instructors, again, this is my list of instructors, and I can show you the values for this. So Jesse, Dave, Wes, Stephanie, and C Hacker. And what I want to do is for each instructor in that list, so for each variable, or sorry, each value in that list, I want to do something with it. And the question earlier about indentation was really important. And so it's really important that we indent this. Otherwise, the print statement is not part of the for block. So the same rules apply. And the other thing I want to draw your attention to is this thing instructor. And so this is basically a variable, the value of which will get substituted in to each one of these in order and then passed to the print function. So, you know, let me just run it and then we can decompose it afterwards. So in this loop, what's going on is the first time through the loop, Jesse, which is the first element in the instructors list, is being put into the instructor variable. So the instructor variable is essentially set to the word Jesse. And then when the print statement runs, it prints out Jesse. So the second time through the loop, it sets the instructor variable to Dave, and then the print comes out with Dave. And then the same with Wes, Stephanie, and C Hacker. And because a list is an ordered collection, these appear in the order that they were put into the list, right? So this is sort of the fundamental concept of a for loop in the vast majority of Python, is to iterate over elements in a list, or elements in something that's an iterable, or something that looks or behaves at some level like a list. Okay. The other thing I want to point out is that at the end of this, so at the end of this, when this loop is done executing, this variable doesn't go away. So it remains. And we can actually look to see what it is at the end of the list. And it remains the last element in the list. So when we run out of instructors, this list exits and moves on to the following statements and leaves the last value of the list there in the variable instructor. So cool. Now you have some idea about how the for loops work. And the other thing I want to mention is that you can combine all these concepts, right? So we can loop over the elements of the instructors list. That is, you know, what was it? Jesse, Wes, or Jesse, Dave, Wes, Stephanie, and C Hacker. And then for each element in the list, we can do all kinds of stuff with it, right? We can do if statements. We can call functions like we were doing up here with print. So we can go hog wild with each element that we want in our list of instructors. And so if we look at this, let's just unpack it kind of quickly. Again, this is what we saw before. So we're going to iterate over each one of these. So the value of instructor will be set to Jesse, Dave, Wes, Stephanie, C Hacker, respectively. And each time it's going to use this if statement. And if it evaluates to true, it'll print this out. And if it evaluates to false, it'll print this out. Okay. Now here we're using a function or a method on the instructor variable. And we're saying, hey, if it ends with the word hacker, then do something. And again, what I love about this is that it reads kind of like English, right? for instructor and instructors, if instructor ends with hacker, right? You kind of are reading like you would read out English. So let's do this really quickly and see. Yeah, so we got Jesse with all his gooey brains, because when we had Jesse in there for instructor, it didn't end with the word hacker. So yeah, he's got some gooey brains there. And apparently so do I and Wes and Steph. But C hacker ends with the word hacker, and that sounds like a fake instructor name. So we can combine our for loops and our if statements to get really complex behaviors. And so this is why flow control, which sounds so awesome, is so awesome, because it really allows you to change the order and how things are executed in your code. And that's kind of the bee's knees when it comes to writing code. All right. One thing I want to mention about dictionaries, just so that we have it in the back of our mind, is that there is this function on a dictionary called keys. And if we call that function, it returns what is effectively a list of all the keys in our dictionary. And so in this case, what we're doing is we're saying for each key in this list of the keys in our dictionary, if the length of the key is longer than 4, meaning 0, 1, 2, 3, 4 elements, then print it out. Okay, so again, before you run this, what do you think this will print out? So we're gonna, first key is gonna be set to pickles, and the word pickles is longer than 4 characters, so it's gonna print out the definition for pickles, right? Because this gets the definition based on the key. The word list is not longer than 4. It's actually equal to 4. So this will evaluate the false. So it won't do anything for the word list. And when we encounter the word dictionary, the key dictionary is longer than 4, therefore it will print out the value. So let's run that. I hypothesize that it'll talk about small cucumbers in brine or salt or whatever, vinegar, and then it'll talk about dictionary being a collection of elements with key value pairs. There we go. So again, we can combine these ideas of iterating over elements in data structures with if statements and get really complex behaviors out. All right, so you've actually heard us all talk about the word range from time to time, right? And I've said things like over the range of elements. And that's because range actually means something. So range is a Python function that's really helpful in helping us go over things that are iterable. And so when I type this range, what it's actually doing is it's creating a range of values that start at, implied, start at 0 and go up to, but not including 3, right? So when I ask for a range of 3, the 0 is implied, meaning start at 0, and stop before you get to the value 3. And so this here is the same as this, effectively. They are identical. And it may look weird because this doesn't look like a list. You're saying, well, Dave told me that lists are things in brackets, and this looks like a function or something. It looks wonky. Well, it turns out that this is a performance improvement that was made, is that this, instead of actually creating a list of values from 0 to whatever, that this is a special kind of variable type. But in your head, you can essentially manage it like this. And the reason that this was done really quickly for folks is that if I ask for range of something like that, and it created a list that went from 0 to, I don't know, whatever that number is, that big number is, that would take up a lot of memory, right? Because I would have to allocate memory for each element in the list. Whereas this just creates a data structure that represents the range from one number to another. But I can take a list and convert it, sorry, I can take a range element and convert it to a list by casting it. So here I'm using this list function, which casts the element of range into a list. And so if I run this, I see kind of what I expect. Okay, so the take home from this that I really want you to understand is that using the function range with a number is effectively like creating a list that starts at 0 and goes up to, but not including that number, okay? So I can do things like create a list here with, I don't know why I'm doing it up here, I should do it down here, where I have color coding. So I can create a list here of 3 elements. And then for each element in that list, well, not for each element in the list, but for each element in the slice, check to see if that value is less than something or print it out. Otherwise, take no action, right? So that's cool. But usually I want to do something like use a range variable here. And so here's what I've got, where I've got an index into my range. Index into my range because my list of instructors is of length 5. Therefore, I want 0, 1, 2, 3, 4 as my indexes. So remember, range 5 will evaluate to a list 0, 1, 2, 3, 4. And so this will allow me to iterate over them just as we did earlier, right? And so it goes in here and it says for index in 0, so this is going to be 0. So index equals 0 for instructor equals instructors of index 0. So remember that this is going to be evaluated to Jesse because the first index in our list is Jesse. And then when it'll do the thing, and then up here, this index will evaluate to 1. And then it'll look up and that'll be Dave. And then when it's 2, that'll be 3, and so on and so forth. Cool. Yeah, that's the concept of range. This is not actually all that great of an idea because I have to know a priori how long the instructors list is. And really what I probably want to do is get the length of the instructors list. And the length of the instructors list is 5. And then use the range in here. So this will evaluate to 5, and then that value of 5 gets stuck in the range, and then we have effectively the same code as up here. But why is it better to use this approach versus this approach? And that's because the length of the instructors could change at any time. And so this is a much more thoughtful and portable way to do this than hard coding the number 5 in here in case we added another instructor. Okay, so the general form of range is to use this where you have the upper bound, non-inclusive, right? Although if you want a different start that's not 0, you can substitute the value in here. So for example, this is going to give me 1 through 9, and let's actually range 1 through 9 so that you can see. Convert it into a list, and so you can see because I specified the started at 1, it list started at 1 instead of 0. And you notice there's my 9 and it stops at 8 because it's not inclusive. Okay, so that's range. And let's see, you can nest for loops. And so here I'm counting over the numbers 1, 2, 3 in this loop. And then inside of this loop, and you can tell that it's nested, meaning it's inside because I have a tab here. I'm now with the variable j counting over the numbers 1, 2, 3. And then here I've got some fancy code that substitutes in this print statement here the current value of I and the current value of j. I'm not going to go into how this formatting works. There's a link here, and you can go and look that up on your own. But suffice it to say, what this will do is substitute in the variable I for the value I in here, the value for j in here, and so forth. And so we can nest these for loops, and we can execute them again mentally, but then see how it executes here. And so this is I. Remember, we have I, and then this is j. So the first time we hit a print statement, we've got I equals 1 and j equals 1. And then the second time, this loop here executes again without going into the outer loop. So we can see the j has changed, whereas the I is held fixed. And then we have the j has changed again and the I is held fixed. And then we've hit the upper limit for this for loop. So we pop back out into the outer for loop, increment the value of I here, and then run that inner for loop all over again. So there's our inner for loop running here, here, here. And then we we pop back out to the outer loop and increment the value of I, and then increment our j and j and j. So we can nest loops as much as we want, and it can get pretty crazy and hairy. But nesting loops is, again, a pretty common pattern that you'll see over and over and over. All right, I think I want to I want to, you know, a lot of these things I think are useful, and I can, you can probably read through the text to kind of get them on their own. I will quickly just say that break is a way of, this break attaches to this loop, so that when I'm running this loop, if I is equal to, so the double equal sign means equal to, is I of equal to 4, we hit break. So this is going from the number 0 to 9. And when we hit 4, it's going to exit. And so if we do that and we run this, you can see that the value of I after it ended was the value 4. So it didn't bother counting 5 to 9, right? So we can exit out of loops early. Sometimes you might want to just kind of skip over a thing in a loop. And so here we're saying for the numbers 0 through 9, if the current value is I, then don't do anything. Otherwise, add this to the sum. So we've created a variable that has a sum of 0, and then we're adding all the numbers 0 through 9 except 5. When we hit 5, we don't add that to our sum. And then at the end, we print out our sum. And so here's the variable, here's where we're printing out I, and so we can see 0, 1, 2, 3, 4. And then suddenly this condition was true, and so this statement didn't execute. Instead, we popped back up into the for loop and incremented it to 6, 7, 8, 9. Okay, so you have this concept of break, which allows you to leave a loop, and continue, which allows you to skip an iteration in the loop. All right, and then you can always try to iterate over a lot of different things, anything that's iterable, and it turns out the strings themselves are iterable, and they are basically like a list. And so here I've got my string is caffeine, and if I try to iterate over the string, I get each one of the values or each one of the letters of my string. So in a way, kind of strings are themselves kind of lists of letters. All right. Yeah, and so I want to, I went quickly through break and continue. They are incredibly important points. I don't think you need them for the breakout, but I want you to be aware of them, and you can go back and consult this notebook at any time. I've talked a lot today about things like, I think I've said the word Pythonic a few times, and I've talked about style. And there really is a Zen or a philosophy of Python. And it's so core that it's actually part of the Python sort of core itself. And there is this module called this. And if I import it, what it does is it actually prints out a poem by Tim Peters, which is the Zen of Python. And I encourage you to think through these statements because they really are intended, you know, things here aren't going to make your code run better or worse or slower or faster. What they're going to do is help you understand how to write good code that can be read by people and machines. Because one of the most important things is that your code can be read by people. And so I love the Zen of Python, and I wanted to leave you with this before we move to the breakout rooms. And I also want to emphasize that there are great comments that are being made in chat. So Wes, one of our instructors, mentioned that continue is super useful, and you'll see it in a lot of flow control, and I completely agree. And Jesse pointed out that continue is not the same as pass. Remember, pass is an if thing, and continue is a for thing. And so although you can nest one in the other, what they do is apply to the last one of that type. All right, so I think you should all go memorize the Zen of Python. All right.
I'll thank Dave for a great tutorial, and I think we'll take a 10-minute break tonight, and then we'll get back to the tutorials, to the breakout room, sorry, after. But if you could, like yesterday, just stay connected. You can leave your video off for your 10-minute break, then Nida will be able to then split you into the breakout rooms.
All right, thank you, Stephanie, and thank you, everyone. Thank you especially to the folks that were answering questions in chat. That was awesome. I really appreciated that.